Okay. So climate data from space. As Vicky mentioned, I'm a professor here in the Department of Meteorology in Reading, and I head up the Earth observation and space part of the department here. And I'm going to be talking for, well, it's meant to be about half an hour. If I go on too long, which I'm prone to do, we'll keep it to half an hour. I'll just set my timer going so that I know how long I've talked for. So I'm going to be introducing climate data from space in very general terms. And it's an area I've worked in for a decade or so. I'm going to be talking about data from space in general, and then what climate is and what climate data are, and why that's a little bit different to data in general. But I thought I would start with something from before the space age. These are figures related to an expedition to the Arctic in 1879 called Jeannette. They were exploring the Arctic. They got stuck in the ice, had 2 winters in the ice, and had to abandon ship. They had to walk a couple of miles to land through sea ice-covered waters. This is a dramatic moment in their bid to escape the ice. This chap, unfortunately, didn't make it. I've got a question for you, though. He's carrying a heavy trunk. Well, what's in the trunk? Well, I like interactive, so I'm asking you the question. Okay, it's not rhetorical. So what's in the trunk? Any ideas? It's obviously something very precious because it's a heavy old trunk, and they're determined to bring it back. Theodolite. Ice. Any other ideas? Yes. So it could be scientific instruments, could be samples of some sort. Actually, it's data. So the guy was carrying a trunk full of logbooks from which these data are extracted. So these are the sorts of logbooks they kept. They kept a lot of meteorological observations. This part of the world is essentially unexplored meteorologically at that time. And in fact, the whole mission was based on the misconception that the North Pole would be ice-free in the summer. And that's why they got into trouble. And I just wanted to introduce it this way because although you might well get data free, environmental data is not actually cheap, okay? There's always effort involved. I'm glad to say that in my line of work, I don't endure some of the risks that these guys did for the sake of the scientific data, but it's a point that we live in an age of big data where lots of data are very cheap to collect. But environmental data of any sort isn't actually like that. It requires effort in the collection and also in the interpretation and adding value of interpretation to that. So that's a sort of basic message that we mustn't take these things for granted. This is the course of the Jeannette as it was making its bid to sail to the North Pole. It's overlaid on the data for sea ice 100 years later. Which is now we're able to measure from a satellite, and you can see very clearly that if they'd had this sort of information then, they wouldn't have endeavored to sail to the North Pole that summer. So, of course, that's an exciting example from the age of exploration, but in some ways the age of exploration, I'd like to emphasize, is still with us. It's really the exploration of the dynamics of our planet rather than just the basic facts about the planet. And a lot of what we are learning still is informed by Earth observation, so observations from space. And in some ways, exploring the Earth from space is in a bit of a golden age for reasons we'll come to later. And importantly, this stuff really matters, and that's why you're all here, I guess. We do depend on the Earth for all sorts of, well, we call them ecosystem services, but it's basically the means to live our life. And we do need to understand the dynamics and our interactions with the Earth, as I'm sure you realize. And then that final point that, although not quite as costly as the people of the Jeannette found their data to bring back, data are still costly, although for the benefit of all sorts of applications, we try to make space data free a point of use as much as possible. There'll be more about that later. So the outline of the serious bit of the talk really is to look at data from space in general, what can be measured, a bit of comment on what can't be measured. We'll then think about climate. This is climate data from space, what characterizes a climate question. we'll look at a definition of that, so some ideas about barriers to use, a little bit on concepts about how to get data to the downstream users, but there'll be much more about that later, so I won't go too much into those aspects, and a little bit of a forward look. Okay, so data from space in general. There are a wide variety of measurements which can be made, and most of these measurements rely on light of some form. So electromagnetic radiation, either visible light, where we're looking at the reflected sunshine, shortwave infrared, which is also reflected sunshine, but just not visible to our eyes, thermal infrared, which you might characterize as earth shine, so the actual emission from the earth itself, and microwaves are widely used. And then there are a few other things you can also measure from space to do with gravity. What you actually measure is acceleration. And the heights of things you can measure by essentially measuring the timing of reflected pulses of electromagnetic radiation. So what you're indirectly measuring there is distance. So I thought we'd start off by zipping through some examples of this wide variety, because I guess many of you are familiar with much of this, but perhaps you haven't seen all of these things. So one very simple, I'm doing this in wavelength, by the way, so I'm starting with what's essentially a visible image. So this is not quite what you see from space. It's been corrected to take out the effect of the atmosphere and give you a synthesis of what you would see on the Earth if you were looking from space without the atmosphere intervening. I think actually for the clarity of the images, at least we do need a bit less light from the back. So if someone could shut some more blinds, I think that would help the quality. Thank you. We will open them again when we get back to the texty stuff, because otherwise you'll all fall asleep. Yes, that's a bit better, isn't it? So you can see there's a geopolitical boundary here, and you can see the difference between a very arid area and an area where, in the same climate, you have quite a different sort of land cover. It's very obvious. That comes to land management practices, essentially, and that's just an example of human interaction with the environment. The picture on the right here is using a combination of red and near-infrared light. You can see that plants turn up green when green plants turn up red when visualized in this way. This is someone's rather nice garden with a swimming pool in it. And of course, that situation can be used to monitor the health of plants. So we have healthy vegetation on this image on the left is in red in the same way. Looks like they started plowing across this particular field because half the vegetation is gone. Those sorts of near-infrared wavelengths and visible wavelengths are also used in looking at some aspects of the atmosphere. Here's an example of carbon dioxide measurement from space. This particular technique only works over the land, as you can see, because it needs a bright background and the sea is quite dark. You can see seasonal cycles. You can see how there's a variation between summer and winter in the amount of carbon dioxide as plants in the northern hemisphere suck up carbon dioxide from the atmosphere to grow their leaves and then release it back when the leaves die off. People quite often assume that this is the sun and that these are sunspots, but that's not what we're looking at here. This is the Earth. Now we've moved longer in wavelength, and we're looking at the way in which the planet actually releases heat to space. So this is Earth shining out to space. If you think about it, you've got sunlight coming into the Earth, and some of it gets absorbed. The planet would just get hotter and hotter and hotter if it wasn't also releasing heat to space, and this is how it does it. It shines in these sorts of far infrared wavelengths. What you're looking at is the atmosphere, and these are the tops of thunderclouds that are bubbling up here. Infrared wavelengths can also be used to... that's my TV playing. There we go. Try that. This is quite a big movie. I think it's just got indigestion. So this is a movie of the ocean temperatures around the Earth, which, when it plays, shows all sorts of interesting dynamics. but it can't seem to get the projector to respond to them. Also, if we go a bit further into the microwave part of the electromagnetic spectrum, you can synthesize essentially large telescopes in space, and some of the industrial folk will be working in companies that have worked on this. Essentially, by piecing together the different signals detected at those different temperatures, you can get a feel for how the emission from the surface varies in space. So synthesizing that aperture. I think that movie's killed the PowerPoint, so we have to restart. Okay. Let's try that one then. And possibly surprisingly, at these long microwave wavelengths, you can even detect the change in the radiation coming up from the sea surface caused by variations in salinity. Now, the saltiness of the ocean water doesn't change very much. There's a very subtle signal there, and this is a movie of the monthly changes in salinity around the sea surface, which is quite a remarkable thing to achieve. So the red bits are saltier. You can see, for example, this is slightly less salty because the outflow of the Amazon comes in there and brings lots of fresh water. So those are all examples of things detected from space using electromagnetic radiation. I mentioned that through acceleration, you can map Earth's gravity. So this is a mission where you've got these two spacecraft, the distance between which is measured extremely precisely. And essentially, if one is approaching a mountain or something that has a bit of extra gravity, it gets accelerated earlier than the one that's trailing, and that allows you to have a signal that maps Earth's gravity. Okay, I'll skip that one. And you can create a global picture of the surface. So if you had a marble, okay, and placed it on the surface, it wouldn't roll. You can see it goes up and down, so the actual distance goes up and down, but this surface is one in which the marble would experience it as flat, which is slightly counterintuitive if you're not used to it, but that's essentially a surface in which it seems to be flat. Gravity is also used to detect the loss of mass, for example, from the Greenland ice sheet on a fairly coarse scale. So that's a sort of whistle-top tour of all sorts of whiz-bang amazing stuff. And it really is quite remarkable, the range of data that are available from Earth observation. And hopefully you've seen something there that you haven't seen before, and it's just a bit of inspiration. Now, it is genuinely impressive, but sometimes there's a bit of a danger in giving a bit of a presentation like that, because potential users get the impression that anything is possible. And this is what we've got to guard against a little. From space, there are things you cannot do, okay? And one very basic thing is you can't measure anything that leaves no signature at the altitude of a satellite, okay? So that's a very fundamental constraint. A bit less obviously, from space you cannot measure at arbitrary times and places. And we'll discuss a bit of the reason for that. It's to do with orbital dynamics. So very simply, we'll explain why that's the case in a second. And for almost every sort of observation, there are situations in which the data will not be available. So situations in which something interferes with the ability to detect the thing you're trying to look at. So not all wavelengths see through clouds. So we know that because we can't see the sun today. Microwaves do see through clouds, but if it's raining, the rain will interfere. That's fine if you're actually trying to measure the rain, because that's your signal, but if you're trying to do anything else, it's interference. And then there is man-made interference at microwave wavelengths as well, which interferes with quite a lot of those sorts of observations. There's also limitations on what you can resolve, what sort of level of detail you can see at different wavelengths. So I just mentioned that microwave radiation passes through clouds, so that's great. Maybe we can do some very high resolution just images in the microwave. Well, there are limits to the resolution you can achieve that vary with wavelength in a passive mode. There might be limits on the rate of repeat, how often you can get a sample. No data are infinitely precise, so there may be limits that affect your application in terms of level of precision of the data. And another fundamental one, as fundamental as the first bullet point really, is that all of these processes are what's called inverse problems. So the way this works, you have the state of the Earth, you have the condition that you're trying to measure, but you're not actually measuring the thing you're after when you're doing Earth observation. That state is influencing radiation or something that you see at the top of the atmosphere. And you're trying to infer what's going on down here from what you observe indirectly. So that's a class of problems called inverse problems. That's a sort of fundamental aspect of these, is that you can't do that reverse process without some fundamental level of ambiguity in the process. And that's why it's a difficult thing to do. So there are these limitations. I'm just going to go a bit more into the reason why we can't observe at arbitrary times and places. So as you know, we have satellites in orbit. One of the two common types of orbit is geostationary. So this is the viewpoint from just behind a geostationary platform. It looks like it's hovering over the Earth. What it's actually doing is rotating around, of course, at the same rate as the Earth in order to keep track. So if you want to stop and stare at a location for a long period of time, you've got to use an orbit like this. Now, this isn't quite to scale. Satellites are somewhat smaller than are illustrated in this diagram. But one thing that is to scale is the radius of the Earth compared to the radius of the orbit that this satellite's whizzing around in. So this geostationary satellite that's going around is something like 36,000 kilometers above the surface. And there's nothing you can do about that distance. Now, that's a fundamental limitation. So in a geostationary orbit, you're going to be a long way away, basically. And that has implications in terms of the amount of detail that you can see. So if, so you probably noticed this guy whizzing around in low Earth orbit. So that's just a few hundred kilometers up above the surface. A lot of remote sensing is done in that mode. As you can see, essentially, just like the other satellite, the platform is whizzing around in a plane, doing a circle, more or less. And it scans the whole Earth because the Earth is rotating underneath it, essentially. Around the course of a year, something else happens, but we don't need to go into that. So therefore, this is why you get this pattern quite often in Earth observation of stripes of data. And what's not clear in this movie is that, of course, if one stripe is in the daytime, you saw the daytime side. The other side's at night. So if you're doing something in the visible wavelength, you've only got stripes on one half of the orbit as well. And there's typically 14 of those low Earth orbits in a day. And in the course of a day, of course, the Earth has rotated one full cycle, and so you get these stripes going across the surface of the Earth. And again, that's a basic, fairly fundamental limitation on the sorts of rates of sampling and places that you can observe within a given time. And it basically comes down to Newton's law of physics. So that's been a bit of a brain dump. I'm going to show you this, and I'm going to ask you a question. So observe carefully. Now, if you've seen these movies before because you know where they come from and stuff, you're not allowed to answer, okay? It's only people that haven't seen this stuff before. Obviously, this is a movie. You can see the cars moving. Does anyone know where it is? Anyone recognize it? Yeah?
It's Dubai.
It is. That's the Burj Khalifa, or yeah, the tallest. Is it still the tallest building in the world? Not sure. That's correct. Now, obviously, time is elapsing here. So what sort of orbit was this movie taken from?
Geostationary.
Okay. Anyone, put up your hand if you agree with that. Okay. Yeah. Okay. Now, the rest of you, presumably, think it's from LowEarth Orbit. Okay. Well, it is a trick question. I always do this to the students. I always ask a question where they're going to get the answer wrong. So thank you for being my stooge. There's some clever image processing going. Essentially, the camera points a bit ahead of the satellite, and as it whizzes past in low Earth orbit, points a bit back, and it makes it look like you're seeing it from a static position, except for the fact that you get this weird parallax effect. You imagine you're looking at something from one side, and then from over there, you get this effect. So it is taken from low Earth orbit, and because this satellite's whizzing around the planet, that's as long as a movie as you can get. So yes, we've got video from space, but they only come in segments this long. And again, that's a basic limitation of the regime of orbiting that orbital dynamics imposes upon Earth observation. So that's just a few examples of how the sampling you get from any sort of Earth observation might not be exactly what you really want. Okay, coming on to climate. So the second part of what I'm going to say. What is climate? Well, climate is the weather you expect. Weather is what you actually get, basically. There are all sorts of aspects of climate. There's not really worth defining it too closely. There are many things that are relevant to all sorts of applications where people don't necessarily think they're doing climate in any sense. The typical one is average temperature for a given time of year. But things like, say, the typical wind profile at a location, you could also view that as something to do with climate. But of course, it's very relevant to people siting wind farms. The probability it's below freezing with no wind in Yorkshire would be very relevant to the energy industry in the context of renewable energy supplies. Sunlight hours expected for a particular field, obviously of relevance to solar energy and to agriculture. So climate is essentially our expectations of many, many aspects of the environment that we might be exposed to and concerned about. Now, climate scientists have a slightly different sort of view. They think about all sorts of timescales, from weather back to 100 million years. It's all climate from their point of view. And when you go to these really long timescales, essentially everything the planet does becomes relevant to climate. So the opening up of a gap between North and South America and the change in ocean currents, for example, would change the climate significantly. Building the Himalayas changes the patterns of weather and so on. So over these long timescales, essentially everything becomes part of the Earth system. Volcanoes is another example. And so it's very difficult to say that there's a particular list of environmental variables that are climate and others aren't. But the common theme is really you want to know how a particular state, a particular condition relates to the longer term. And that's really what we're talking about for climate. So climate data from space, let's not define it too closely, but essentially there's a climate data from space stakeholder group, which is advisor to the UK Space Agency. And when we wrestled with this problem, we decided that it was something that measures an environmental variable over a reasonably long time and that have good consistency over time. The purpose being that you can look at a particular state compared to some sort of evolution over time. So this aspect of consistency over time is really what I think we would identify as distinguishing climate data from other forms of EO data. And if your application requires that recent and past values can be compared with reasonably well-known confidence, then climate data is relevant to you. We wouldn't call it a climate data application if that wasn't the case. But actually, because of this requirement to impose consistency over time, which is not cheaply achieved, climate data are actually highly usable, and possibly better than random data for other applications as well. So for example, just to draw out this distinction, satellite data came into routine use most earliest in the subject of meteorology, so used for weather forecasting. But essentially, after about 24 hours, the relevance of any observation to a weather forecast disappears. And so their prime motivation is to get the data to the forecast system in a timely way. And if some quality is sacrificed in that process, that's less important than missing the data, which would be a much worse outcome. So if you take the time sequences of satellite data that have been used in weather forecasting, you'll find there might be sorts of jumps and inconsistencies over time because consistency over time has not been the priority. So a climate data set would be one where it's been reprocessed, typically, to do something about those inconsistencies over time and create something where you have a more accurate ability to compare any given time to the whole record. This is sort of a developing area. The way in which it's worked essentially so far is that people interested in climate change over, say, decades, people like me, have gone out and got funding to reprocess historical satellite records. And one project that I'm involved in is ESA's Climate Change Initiative. This whole climate data from space thing really emerges from the fact that having done that, because of their high quality, these data are potentially useful to a much wider pool of users. And one thing that's been recognized is that it might be possible to make those data work for climate services, including commercial services as well. But there is additional activity needed to make this happen in practice, I'd say. Richard will be going into this much more later, but to get from science to services, we need to recognize that climate expertise is required to make the climate data from space. But scientists doing it for their own academic studies don't have the same priorities necessarily as anyone wanting to build some sort of service on the data set. So for example, we might not be as worried about timeless. We might be happy to process 20 years and then work on it for a year or two before we do any more, until we get the paper out, and then we might do a bit more and update it with what's happened recently. If at any given point in research a bit of data is missing, it's possibly not the end of the world, but if it's what you really want, the day you want to look at your climate service data and it's missing, then that's obviously a very bad thing. We're happy working with specialist formats, but really to get the data much more widely used, to potentially any potential user, it needs to be much more accessible. Research is funded in 3-year blocks, typically. And at the end of the 3 years, if you haven't got any more money and your postdoc leaves you, then you don't do anything for a while until you manage to get the next set of funding. So that sort of stop-go production of data is a bit of a barrier to building any sort of business or exploitation on top of data. And scientists know that data are valuable. That's why I started off the talk with my Jeanette example. We also realize that every piece of data has uncertainty associated with it. And it's very tempting if you've got a nice looking data set just to treat it as perfect. And I would caution you not to do that because it's never the case that it is. So don't be naive when you come to data. Just recognize that it's reducing your uncertainty but not eliminating it. That's always the way to handle it. Nonetheless, despite those caveats, it is recognized that we would like to build a seamless supply chain of climate data from space. The concept would be to meet everyone's needs in an efficient way, from the scientists with nerdy applications in climate science through to policy and business. Is it possible actually to deliver the sort of data we want to meet the variety of levels of user expertise in a variety of different forms, and integrate with tools for tracking the provenance of data, quality assurance, visualization. These things will come back, I'm sure, in the course of today. We'd like, now you can't actually see, there's a sort of sweeping arrow coming up here, okay, through operations to value-adding services. So we've got data coming in here, lots of useful things happening over there. And that's all that users will tend to think about as being the seamless supply chain. So you've got data coming in, people process it, you can build stuff on it, and lots of good outcomes happen. But it's not really possible to have that seamless supply chain without this bit sticking out at the end here to support that seamless supply chain of data. And that's because although Earth observation is a greatly advanced technology over the last 30 years, we're still really not at the stage where everything's going to be routine. So there still needs to be research and evolution of how you deal with the satellite data behind anything that we can currently create. I'm sure Richard will talk about this sort of stuff, so I'm going to skip those. Some tips, getting started if you haven't got into the use of Earth observation data before. I think we're still at the stage where it's very useful if you can find someone who knows a bit about the data you're looking at to talk to, just to help focus your thinking on what you need to know. Because if you try and extract the relevant bits of information from all the stuff that's out there yourself, it can be quite difficult to find the key things that you need to understand for your particular application. Don't expect exactly the data you want. Don't be closed-minded about data that are nearly what you want but aren't quite, because the game here is always not to solve all your problems. That's not going to happen. But the game is to reduce the uncertainties in what you're facing. And data can do that, but it won't eliminate them, like I said before. And actually, people producing data are interested in new applications, new uses that they haven't thought of, because that creates new requirements and creates new opportunities for research questions at their end. So this sort of day, I think, is very useful in getting people together to articulate really what they would like. I think we are at the beginning of a new data era in some ways. This is the Earth observation satellite fleet of the European Space Agency. And until recently, essentially, there were meteorological missions. As I said, those were the earliest missions really embedded in routine use of satellite data. And then there were the Explorer missions, which are cutting-edge technology. A lot of the stuff I showed you earlier comes from Explorer missions. And in between, in the last couple of years, we've got the Copernicus Sentinel missions, which are going to be providing data for 30 years and in a consistent way. And that's really the first time we've had sort of cutting-edge observations sustained for that period of time. So less of a stop-go type of data supply. And I think that would be quite transformative in our attitude to sustained observations. I'm not going to go through what all the Sentinels do. This is an EU program, and it is to which the UK has contributed, its fair share of building these instruments. So let's hope that we find some way of getting the data from them, having paid to launch them. But I'm confident that will happen. As well as the space segment, which is illustrated here, there are a number of ground segment operations. So there's a marine environmental service. There's also a climate change service. And there's a land service and an atmosphere service as well. And these are meant to tackle this problem of getting the data into forms that users can use. And so in the example of the climate change service, there'll be sectoral information systems built on climate data stores, where the sort of climate data I've been talking about are the foundation for the information that any user, any EU citizen or EUMETSAT member country, or ECMWF member country can access. So this is spinning up now, and as part of this ongoing effort to realize the benefit of these sorts of data, not just for science, but for a wider range of applications. There are a number of different data sets available through this ESA Climate Change Initiative program. As Vicky mentioned, this is my project here, the sea surface temperature one, but there are a number of other projects there, and there will be, we hope, involvement of the UK in the next phase of the Climate Change Initiative, which should be kicking off in a year or two. Again, there are data there. This portal goes some way to meet this question of accessibility. You'll get another example of a means of accessing data when you do your workshop on the PML system a bit later. So things are beginning to come together, I think, from a user's point of view, but it's still very much a concept that's being built. So I'll just finish with some key points, then I can take any questions you have. The key point when you're thinking about climate data, does your application need comparability over time? Not that necessarily climate is the focus of what you're doing, but climate data can be used for a wider set of applications for that, where comparability over time is important. We have huge EO capabilities. At the present time, getting that out into all sorts of applications is still a work in progress, and there are real efforts to change this and address barriers, some of which I've mentioned and more of which you'll hear about. Dialogue between EO specialists and potential users is very valuable, and it will help advance this realization of the seamless supply chain that will meet a wide variety of our needs. So that's the end of my presentation. I've used up all my time, but I'll leave it to the chairs to decide whether I can take any questions. Thank you.
I reckon we will take a couple of questions if people have any. Because I have a question. So
Sure.
we're talking about, so you deal with sea surface temperature data. So has anybody ever approached you directly to get data from you?
Yes.
And what sorts of people are they?
We had someone from a coastal, I can't remember the institute, but a sort of fisheries institute who wanted data, and CEH of Wallingford have also been in touch about data as well in the Thames estuary. And it was an interesting case because essentially since those interactions, we've put on our website a very simple tool that allows you to click a point on the map and you get a spreadsheet with a list of numbers in it, which is the SST, which is not something that as a scientist I would ever have thought of doing, because we would never use a spreadsheet, and but that's the most convenient form for those particular people, and there's been a reasonable usage of that sort of thing, and that's a very simple example of how things can be joined together when people actually do communicate with each other about this sort of issue.
So in a way, then it's worth asking.
Yes, absolutely,
Yeah.
yes.
If you know who the person
Yeah,
is.
that's the problem. As I say, I think we're still at the stage where it is helpful to find someone who knows something about what you're interested in. We're still at that stage where you can't just do a Google search and necessarily find exactly what you're after.
Any other questions?
Yeah, I guess on that sort of same effort of collaboration, do you get involved with sort of the catapult, the setups catapult sort of elements for creating engagement with different sort of parties and stuff?
Yes, we have a bit. In fact, we've just got a spin student come to work with us over the summer, which was arranged through a catapult event to look at thermal pollution around the coast. So from some big installations that send cooling water out into the sea, and what we can do on that front. So again, not something as a scientist I'd have thought to go and look at, but it's quite interesting for us to look at that sort of thing.
Okay, one final question from Ken. And then
Yeah, just briefly, you mentioned that the climate data store, the ESA climate data store is being spun up now. Do you know when that? So
there are two things. So the ESA Climate Change Initiative portal is being spun up, and that's sort of really developing, now. So there are data on it now, that's fair to say. And that's just serving the ESA project data. And then the other thing, the Copernicus climate change, so this is a bit complicated. So this is run by an organisation called the European Centre for Medium Range Weather Forecasting, which is based in Reading. And they're building this climate change service here. It's part of the Copernicus programme, so it's an EU project. And that's really started about a year ago, and they're at the stage of building the infrastructure, really. And they haven't actually started importing data yet. I think that should be spun up within a couple of years. They have some demonstrator projects for particular sectors that are ongoing. I can't remember what the sectors they've called for first are, maybe agriculture and energy, yeah. So they're still learning how to do this. I would say that if by year 4 they have something that is at the level where users can come in and do stuff really, really easily, then they'll have done quite well, because it's a challenging thing to do.
Thank you very much.
Great.